This particular session is useful for all those students who have opted for doing BSc program major in chemistry, or who have opted for two of the courses in chemistry, that is organic chemistry and the organic reaction mechanism. So, organic chemistry is the CHE5 course, and organic reaction mechanism is CHE6 course. For this particular session is related to both organic chemistry and the organic reaction mechanism. The organic chemistry, if you have already opted and you have gone through, you would realize that this generally is related to the qualitative concepts of the organic reactions, whereas the reaction mechanism deals with the mechanistic part of all the reactions in detail. So, the concepts which are generally dealt in organic chemistry are related, and we in fact have advised our BSc students to opt for organic chemistry prior to studying the organic reaction mechanism course. You are aware that organic reactions are basically categorized into addition, elimination, rearrangement, free radical, etc. So, if we start our today's session, which will be related to the chemistry of carbonyl compounds, and here I would like to just mention one more thing, that the chemistry of carbonyl compounds, as I was saying, the qualitative aspects have been dealt in organic chemistry course as well as in the 6th unit of reaction mechanism. So, you will find that the factors, the concepts like the preparation, the properties and the reactions which are dealt in organic chemistry are dealt in detail from the mechanistic point of view in the reaction mechanism of these compounds. Now, if we see carbonyl compounds, we know that carbonyl compounds are the compounds which have CO group as shown here in the molecule. Now, in carbonyl compounds we have two types of groups. We have aldehydes as well as ketones, and aldehydes are the ones where at least one of the groups is, or one of the atom is hydrogen, the other may be hydrogen or any other alkyl group, but then this carbonyl group should always, this C double bond O group should always be there. And for ketones we have two alkyl groups along with this carbonyl group. In the chemistry of carbonyl compounds, there is another category which are carboxylic acids and their derivatives, but the chemistry of carboxylic acids becomes quite different as compared to the aldehydes or ketones because of this leaving group, which is because of a good leaving group here in place of H or R. The properties, the chemical reactions shown by carboxylic acids are very different. So, today's session we would in fact be considering only the carbonyl compounds, that is aldehydes and ketones. And why have we really chosen only the carbonyl compounds? We know that carbonyl compounds are very important to an organic chemist, and because most of the a number of them are used as solvents and are very good solvents. For example, maybe you know acetone, which is by a very I think which is used by a number of females for removing their nail polishes, and very popular as the nail remover. And similarly we have aldehydes, which is very important for a biologist, because formaldehyde is a 40% solution of formaldehyde is used in the form of formalin to preserve their specimen. So, that way it is very important for biologists also. Then besides this, the complex compounds of complex carbonyl compounds are used variedly, like the food additives, the carbohydrates and a number of steroids. My colleague and the co-presenter Dr. B.I. Fauzdar will like to elaborate on these aspects, and I would request him to go further.
In this the compound, you see the first compound, this is the cinnamaldehyde. This is used as a perfume and as a additive, food additives. And the second compound is vanillin, which everyone is familiar with this flavor. It is used in the vanilla ice cream and is also used as a food product for other food. The second is citral. This is also a citral. This is also one of the important food additives. And the next compound is helminthospoporil. This is used for the chemical warfare. This is a highly toxic compound, and other compounds like carbones and camphor is also used as a flavoring agents. And other compound is muscon, which is found in the musk deer. It is also a flavoring agent. Then there are three compounds like testosterone, progesterone and cortisone. These are the hormones which play a very active role in our biological system. Carbonyl compounds have many, as my colleague discussed, have many industrial and synthetic applications. Indeed, the chemistry of the carbonyl compound is considered to be the most important in the organic chemistry. Today, our focus will be on nomenclature of the aldehyde and ketones, structure and physical properties, important preparations and important properties of aldehyde and ketones. Now we will take up the nomenclatures of aldehyde and ketones. We are taking up this because we want to familiarize with the few important simple aldehydes and ketones. In common name of the formaldehyde is derived from their acid derivatives. Like formaldehyde, it's derived from the acid formic acid, and similarly acetaldehyde is derived from the name acetic acid, and then benzaldehyde, it is derived from the benzoic acid, and acetone and benzophenone. In IUPAC names, we treat aldehydes as the derivatives of alkanes, alkenes and alkynes, while ending E of the alkane is replaced by -ul. Like alkanes is changed to the alkenyl. So this formaldehyde now we call in IUPAC name is methanol, then ethanol, and 3 carbon compound is called propanol. Now we are taking one exercise. What will be the name of this compound? This is a 4 carbon compound, so it's a butane, and because it's having a aldehyde group, now it's called butanol. Similarly, now take the another compound. This is a 7 carbon compound. It is heptane, and it is having a aldehyde group, carbonyl group at 1 position. So the name will be 4,6-dimethyl heptanol, because at 4 and 6 positions methyl group are there. Aldehydes not readily named after the alkanes are instead called carbaldehydes, like this cyclohexane carbaldehyde, and this is another example. It is called 4-hydroxy 3-methoxy benzene carbaldehyde. Similarly, in IUPAC name, ketones are treated as derivatives of alkanes, alkenes and alkynes, and the ending E of the alkane is replaced with ONE. For example, this is a 3 carbon compound, propane, and now it is called, because it's having a carbonyl compound, is propanone. And next is pentanone. It's having a 5 carbon, it's derived from the pentane to pentanone. And similarly, this is called benzyl ethanone, and in common name of this compound is acetophenone. Now we are giving an exercise. What will be the name of this following compound? You see this compound is a 7 carbon compounds, and ketone group is at the 3. For numbering, we done from that end which is very close to the functional group. So it is having a 1 methyl group at the 6th position and 1 chloro group at the 4th position. The name will be now 4-chloro-6-methyl 3-heptanone. Now we are taking up the structure of the carbonyl compounds. Carbonyl compound having a carbon oxygen double bond, as we said earlier, and it is having a 1 sigma bond and 1 pi bond. The difference of this carbonyl group from the carbon-carbon double bond is that here oxygen is more electronegative than the carbon, and it is also having a 2 lone pair electrons. Because of this, carbonyl compound is totally differ from the carbon-carbon double bond, and their chemistry is very interesting. Because of this polar nature of the carbon-carbon double bond, oxygen having a partial negative charge and carbon is having a partial positive charge. Because of this, nucleophile, which is a electron rich compound, is like to react with the oxygen. Similarly, carbon is having a positive charge, electrophile carbon react with the base and nucleophiles. And another property, important property of the carbonyl compound is they are having a acidic nature of alpha hydrogen. Before going to the detail of the chemical behaviors of the carbonyl compound, let us study its some physical properties and spectral properties. Physical properties. Here we have taken a few examples, like this is propene, and next is this propanol and propanol, and this we have taken example to compare their boiling points. You see, propene is having a -47 boiling point, and propanol having 28.8 degree, and propanol is having 78.3. In the case of the propanol, there is polar interaction because of polar nature of this compound, and in case of the alcohol we are having polar interaction as well as the strong hydrogen bonding. That's why it is having higher boiling point than the aldehyde. Similarly, we have taken 3 other examples having a similar structure. Here you will see they are having a boiling point in between the alkene and alcohol. This is, we can say that because of the polar interactions, they have this type of boiling natures. Now come to the spectroscopy. Now we are taking first IR spectra. In IR spectra, we have 2 characteristic peaks for carbonyl group. One because of the CO stretching, and other is CH stretching in case of the aldehyde. Such signal is not possible in the case of ketone. The CO stretching is generally range around 1700 to 1740 centimeter inverse in the case of the aldehyde, and ketone it is around 1660 to 1750 centimeter inverse. To illustrate this, we have taken an example. This is the IR spectra of a ketone, and we are having a very characteristic signal you can see at 1715, and this is the all. Now we take the NMR spectra. In NMR spectra, compound having the carbonyl group, this we have taken an example of ethanol. In this case, we are having a signals for the CH3 at around 1, and for the CH2, because of the electronegativity of oxygen atom, this proton, CH2 proton, is downshifted, and it is around 2.5, and CH proton of aldehyde group is around 9.10. Now take the UV spectrum of a carbonyl compound. This is a spectrum of 1-acetyl cyclohexene, and we have very characteristic signals here for pi-pi transitions and n-pi transitions. You can see in this spectra, in the first spectra, we have shown the pi-pi transitions, and the n-pi transition is actually forbidden transitions. So this is only visible in high concentration. Now we are taking the preparations of aldehyde ketones. Aldehyde and ketone can easily be prepared from the alkanes by ozonolysis. You can see here carbon-carbon double bond is react with the ozone, form a ozonide, and ozonide on decompositions give a aldehyde and ketone. Is depend upon the starting material. In the same way, it can be prepared from the alkenes by hydration method in the presence of the mercury ion, and we can prepare aldehyde and ketones from alcohol. Alcohol can be oxidized to aldehyde. For this we have to use selective reagents, because aldehyde again oxidized to the carboxylic acids. So different type of oxidizing agent we used are given here as acidic potassium dichromate solution, hot concentrate nitric acid, chromic acid, and chromium trioxide complex with pyridine and HCl. This is also called pyridinium chlorochromate, PCC. Here we have shown a reactions of this complex. This react with the primary alcohol, give the aldehyde. And in another example, we are oxidizing a secondary alcohol to a ketone. We can also prepare aldehyde and ketones from the carboxylic acids. When calcium salt of carboxylic acid we heat, we get the aldehyde and ketones. The nature of aldehyde ketones depend upon the starting material. If we are started with the calcium methanoate, we will get the methanol, and we are using a mixture of calcium methanoate and calcium salt of other carboxylic acid, we will get the aldehyde. And if we start with the calcium salt of the carboxylic acid, we will get the ketone. Aldehyde and ketone can also be prepared by the reaction of the carboxylic acid with manganese oxide. Here in this case also the product will depend upon the starting material. If we are starting with the methanoic acid, then we will get the methanol. If we are starting with the methanol and carboxylic acid mixture, then we will get the aldehyde, and if we are starting with the carboxylic acid, then we will get ketone. Aldehyde and ketones can also be prepared by the acid chloride using Rosenmund method. In this method we use palladium as a catalyst and barium sulfate. Barium sulfate is actually used to stop the reaction at the level of the aldehyde. We will not get the other product. And it can also be prepared using the Stephen's method. In the Stephen's method, we use alkyl cyanide and SnCl2. This give the aldehyde. And aldehyde and ketones can also be prepared from the Friedel-Crafts acylation reactions. In this benzene is alkylated using aluminum chloride, and we will get the ketone. Now we will take up the reactions of aldehyde ketone. I request Dr. Lalita S. Kumar to continue the discussion.
Thank you, Dr. Fauzdar. I hope you have got an idea how carbonyl compounds are prepared and what are their physical and spectral properties. You have seen what are the specific features of carbonyl group as well as the groups which are attached to the carbonyl group. And in fact, as Dr. Fauzdar had shown the structure of a carbonyl group per se, the carbonyl group, though we can compare it to the alkenes, and it also undergoes addition reactions, but due to the polarity of this carbonyl group, we find the reactions which it undergoes are quite different from the ones which generally alkenes undergo. And because this carbonyl is polar, and the polarity is in such a manner that oxygen is partially electronegative and the carbon being partially electropositive, we have carbon as the center of nucleophilic attack. So the very first thing is that it will undergo all the nucleophilic addition reactions onto this carbon. Secondly, as I said, that it is different from the alkenes in the sense that there is a polarity, whereas in case of alkenes, since you have carbon-carbon double bond, so there is no polarity in the bond and the reactions are different. There is another aspect of carbonyl chemistry from mechanism point of view, and that is again dedicated to the polar nature of this carbonyl group. This carbonyl group, because of its partial positive character, it makes the alpha hydrogen, that is the hydrogen attached to the alpha carbon to the carbonyl group, becomes acidic. It becomes easy, we will see how to remove this hydrogen atom, and by virtue of it undergoes a number of reactions where this hydrogen gets eliminated and the reactions take place in different manner. And broadly we classify the reactions of aldehydes and ketones into 3 or 4 types, you can say. First is the reactions which are specifically for the carbonyl group, where the addition reaction takes place to this carbonyl group, and then we have reactions involving what I mentioned as the acidic hydrogen, that is the alpha hydrogen, which is attached to this alpha carbon, and also the carbonyl compounds undergo oxidation and reduction reactions. Oxidation gives rise to acids, and reduction obviously goes down to the lower and forms the alcohols. The reactivity, if we compare the reactivity of aldehydes and ketones now, we have already mentioned that the basic difference between an aldehyde and a ketone is that one of the groups attached to the CO group has to be hydrogen, or the atom has to be hydrogen in case of aldehyde, whereas it is both the alkyl groups in case of ketone. Now, how do these groups affect the reactivity of aldehydes and ketones, and that is the reactivity, first of all we know that depends upon the polarization of carbonyl group, and there are two alkyl groups in ketones, and we know that alkyl groups are electron donating. They are the delta positive on carbon is being shared by these two alkyl groups because they are electron donating. As a result, they lower the positive nature of this carbon, that is the nucleophilic attack, it means will not be as effective as it is in case of aldehydes, where we have only hydrogen here which is not able to donate any electrons towards the delta positive of carbonyl group. And there is another effect of these two alkyl groups, that is the alkyl groups being bulkier as compared to one alkyl and one hydrogen. They cause a lot of steric hindrance, and we know that after addition this double bond, this sp2 carbon will get converted into sp3, and after getting converted into sp3 it will have more groups, and those groups if are along with these two alkyl groups, they cause more of crowding, again a negative factor for the reactivity of ketones. So, in general we can say that ketones are less reactive as compared to the aldehydes. Now, taking into consideration first the reactions of carbonyl groups, the carbonyl group we said earlier, these are attacked by a nucleophile, or there is a possibility of attack of the electrophile also. The reason being the carbonyl group has delta plus and delta negative both, and when it is a nucleophilic attack, then the attack is first at this carbon forming the nucleophilic the nucleophile substituted attached to this positive carbon, O negative left like this. In the second stage, this O negative gets one proton from the medium and gives OH, or since there is increase in crowding ongoing from what I mentioned is written here, there is crowding in case of the ketones, so the reactivity is generally lesser. And when there is electrophilic attack, then the attack is first at the electronegative oxygen, like in this case oxygen attacking the H plus and giving rise to this species, which is then attacked by the nucleophile. So, here it is just the reverse of what happens in case of an in case of nucleophilic attack. There the attack was first by the nucleophile, here the electrophile attacks first and then the nucleophile. So, if we take a specific case of carbonyl group, that is reaction with water, or we may call it as hydration, and groups like water, ammonia, etc., they form a reaction of the kind where there is equilibrium. So, generally they are not of much significance, but just to illustrate how does the reaction go here, we would take this up. You see, the carbonyl group is being attacked by water. As a result, we are getting a dihydric alcohol, and the mechanism for the reaction depending upon whether we have a base or an acid first is like this. See, if we have a strong base or a strong nucleophile, it will first attack the carbon, the delta plus carbon, the electron shift will be like this, and at the second stage this oxygen will pick up one proton from water and OH gets eliminated. Then of course there is the attack of the formation of the product. And under acidic conditions, because we have a proton available and an electronegative oxygen, so this oxygen takes this proton and first gives a O plus species, which is in equilibrium like this as shown here. At the second stage, then the lone pair of the water molecule, the OH group, attacks here to the positive carbon, and it leads to the formation of the dihydric alcohol. The two OHs are being formed in this manner. Well, in case of formaldehyde, the reaction with water goes with almost 100%, this reaction goes, and if we take acetaldehyde, the reaction is almost 58%, whereas in case of ketones the reaction is much slower. We mentioned that the aldehydes and especially the least sterically hindered carbonyl group in case of formaldehyde gives the fastest product, whereas in case of acetaldehyde and ketones the reactions are relatively slower. And if we compare, now this is two methyl groups in this ketone, and here we have CF3 groups attached to this carbonyl group. The CF3 group is highly electron pulling, that is it makes this C plus center all the more C plus and unstable in the sense it makes it so positive in nature that there is the reaction becomes much faster. As a result, the hydration is almost it is 100% it goes, whereas in case of acetone we have seen that the reaction is only 0.14%. So, this shows that how does the nucleophilicity basically of this carbon of the carbonyl group is affected by the presence of other groups. Now, with alcohols, it forms in case of aldehydes we get first a hemiacetal, that is the OH group attacking this carbon, and finally another molecule of alcohol attacking and giving acetal. The mechanism, as you can see here, it is basically it is in presence of acids. So, first attack of oxygen and it takes that H plus ion and gives OH group, and this is the way. At the second stage, then the second molecule of alcohol through its oxygen with lone pair attacks the carbon plus and gives rise to the this is the hemiacetal, I am sorry, this is the hemiacetal stage, and then the acetal is formed. Okay, with ketones similar kind of a reaction is undergone, where first we get a hemiketal and then we get a ketal, where because we have two R groups here, we call this as hemiketal and this is the ketal. The mechanism is being followed similarly, and the reaction with alcohols has a lot of implication in synthetic organic chemistry. Here the acetal formation or ketal formation is used for protecting via the formation of this acetal or ketal. For example, see 2-propanol, it will not give 2,3-propane diol if we carry out a simple reaction. The reason being, we have a double bond here and we have a double bond here also. So, the possibility of addition reaction is at both the places, because this double bond will compete with this double bond and try to form the addition product. So, one of these, if we want the reaction to be carried out at this place, then this carbonyl has to be protected, and this is done when ethylene glycol is treated with this molecule. We get the formation of this acetal, and the carbonyl group gets protected, and when we carry out hydrolysis we get the two hydroxyl groups getting attached to the alkene group. Then the reaction is similar in case of hydrogen cyanide, the way it is with HOH. Here Cn is the negative part and H is the positive part. So in general the reaction Cn would attack the positive carbon and H goes to the negative oxygen. The mechanism, as you can see, Cn minus attacking the carbon and O negative is being attacked later on by H plus, so that we are getting the cyanohydrin.
I want to add one thing. This cyanohydrin is having a great application in the synthesis.
Okay.
Because we able to add one more carbon to the carbon chain.
I think Dr. Fauzdar, you said rightly, because
we have added one carbon to the carbon chain.
I see.
So if we want to enlarge our carbon chain, so we can exploit this reaction.
Exactly. The reaction with hydrogen cyanide can be used in extending the carbon chain. Okay. Then reaction with sodium hydrogen sulfide. Here again sodium hydrogen sulfide, it forms a hydrogen sulfide adduct, and in fact this reaction is used in separation and purification of aldehydes and ketones, because I think sodium hydrogen sulfide will form an adduct which can be later on, I think,
which can simply convert it into the ketone and aldehyde by simply heating with dilute acid as well as aqueous solution of sodium.
That's right.
Sodium carbonate.
That's right. It means we can easily remove this, and so this is used for the separation and purification of carbonyl compounds.
Now amines also react with the aldehyde and ketones. Primary amine react with the carbonyl group to form a carbinoamine intermediate, and this carbinoamine is a little unstable and lose water molecule to change to the imine. And these compounds also having a very lot of application, because these compounds having a sharp melting point, and these are also crystallized compounds, and we use these compounds for making the aldehyde ketone derivatives which we need for the identifications of these aldehyde and ketones in quantitative inorganic analysis.
I think that is what I was
and we have taken a few examples here. Hydrazine form hydrazone, and 2,4-dinitrophenyl hydrazine form 2,4-dinitrophenyl hydrazone, and semicarbazone form semicarbazoids.
I think they would have done also these reactions.
In the next slide, we have shown how this primary amine react with the carbonyl group. The lone pair of the nitrogen attack on the carbonyl carbon and change to the sp3 carbon, and this carbon having take a water molecule from hydrogen molecule from the solvent system, and again become a good leaving group, OH2 become a good leaving group and forming a double bond with the secondary amine, because in the case of the secondary amine it is not possible to remove water from the carbon and nitrogen bond. In this case secondary amine is react in a different way and forming a enamine. Enamine is basically we also call the vinyl amine. Enamines are very important intermediate products in our organic synthesis.
Another very important, rather synthetically very important reaction, and you would have studied it in your organic chemistry courses also, and would study when you study about the synthetic important reactions, where the carbonyl compounds react with Grignard reagent and form a number of products which have a lot of synthetic value. For example, if we take this, we know that RMgX is the Grignard reagent, where MgX is the positive part and R is negative, contrary to generally what we see are the alkyl group being the positive. Here, so R being the negative, so it gets attached to the nucleophilic, being nucleophilic in nature, it gets attached to the carbon, and OMgX is for the MgX part of Grignard reagent gets attached to the oxygen, and it forms alcohol finally. Now here the application part is that if we take at this place methanol, that is formaldehyde in other words, and treat it with Grignard reagent, what we would get is primary alcohols. Whereas in case of other aldehydes, that is other than the formaldehyde, when we treat them with this reagent, we would get secondary alcohol, and in case of ketones, we get tertiary alcohols. Then Wittig reaction is another very important reaction. Here carbonyl compounds react with the Wittig reagent. This reaction was given by Wittig, so is named like this. Here we make use of halides and phosphorus halides. I think you may be knowing halides are all those molecules where you have a positive and a negative center like this, the one which is shown here. Phosphorus halides can be prepared by, we are using phosphorus halides, they can be prepared by the reaction of triphenyl phosphine with alkyl halide followed by reaction with strong base. You can see it here. The mechanism of Wittig reaction goes like this. First preparation of halide where triphenyl phosphine is treated with an alkyl halide so as to get methyl triphenyl phosphonium bromide. This when treated with a base like butyl lithium, it forms a halide by elimination of a proton. This halide when made to react with carbonyl compounds, it gives phosphoranes which then give rise to alkenes. So, basically the importance of this reaction is in the preparation of alkenes.
Aldehydes can easily be oxidized. On the other hand, ketone need drastic conditions. This difference in the reactivity in the oxidation, we used this oxidation reaction for the differentiating the aldehyde and ketones. Aldehydes can easily oxidize by the Fehling solutions, Tollens reagents and Baradic solutions. Tollens reagent is basically a ammonical silver nitrate solutions, and Fehling solution is a cupric ion complex of the sodium potassium tartrate, and Baradic solution is a cupric ion salt of complex of sodium citrate. Aldehydes react with these reagents, but ketones do not react with these reagents, and aldehyde and ketone can be reduced by catalytic by hydrogenation to the alcohols, and they can also be reduced to alcohols by ionic reduction reagents like lithium aluminum hydride and sodium borohydride. In the next slide, we have shown the mechanism of this ionic reduction. In this case, aluminum hydride having a nucleophilic center and react to the carbonyl carbon and giving a intermediate product, and this on hydrolysis give the alcohol. These reagents are selective in nature. Aldehyde and ketones can be converted into the alkanes directly by the Clemenson's and Wolff-Kishner reductions. In this case, aldehyde and ketone react with the zinc amalgam ZnHg and HCl and they convert into the alkene directly. Similarly, in Wolff-Kishner reductions, first carbonyl group is converted into the hydrazone, and this hydrazone in the presence of the base changes to the alkene.
So, for right now what all we have covered is basically the reactions of carbonyl group per se, which were related to the addition on carbonyl group, and that included a number of reactions. Hope these are clear to you. Then besides that, we have taken into consideration the oxidation and reductions which take place in case of aldehydes and ketones. However, as we mentioned earlier, that there is another set of reactions which are shown by these aldehydes and ketones, and that is because of the acidic nature of the alpha hydrogen, which is very important, and we have a number of other reactions like aldol condensation in that which are again of a lot of synthetic value, and besides that the reactions where we do not have a alpha hydrogen, that will also be considered.